Hi students, so today we start lecture 70 in our aerospace engineering course, and today I'm going to be talking about principal stresses. So this is a very important concept in structural mechanics, and principal stress is something which is going to help us get a handle on the failure theories which we are going to start discussing soon. I'm Dr. Ranjan Ganguly. Now, in the previous few lectures, we looked at the stress state at a given point. So if we look at an aircraft, if we look at any point on the aircraft, then associated with that point is a stress matrix. So the stress matrix has 9 components, but fortunately for us, the matrix is symmetric. Therefore, we end up with 6 components. So it's a symmetric matrix. So sigmas represent the normal stresses, taus represent the shear stresses here, and these are in the x, y, and z direction. So what we are going to do is we are going to look at this stress matrix and we are going to see if we can look at it in a different way. So one of the ways you can do this is to look at this matrix in a different reference frame. So remember that the stress matrix is with reference to the x, y, and z frame or the x, y, and z frame. And what happens is that if we were to change this reference frame to a frame which would comprise of the eigenvectors of this matrix, then we would only have 3 stresses which are there, and these are going to be the 3 normal stresses. So essentially, to look at it mathematically, if I take this stress matrix sigma and I find the eigenvalues of this matrix, it's going to be sigma 1, sigma 2, and sigma 3. And this matrix here, sigma, is essentially the matrix which contains the principal stresses. So what happens is that the eigenvalues of the stress matrix represent the principal stresses. Now, like I mentioned before, the eigenvectors for this matrix correspond to the 3 principal directions. So this is something very important to remember, that the eigenvalues of the stress matrix represent the principal stresses and the eigenvectors of the stress matrix represent the principal direction. So the eigenvalue problem is given by this equation here, that is the matrix sigma multiplied by the vector n equals the scalar sigma into the vector n. So like whenever we are talking of eigenvalues, they are essentially projections of this matrix into scalars. So what we can say is that the information contained in this stress matrix can be condensed into the stress matrix given here. And what happens is that what I had here in terms of 6 variables is now captured with 3 variables by the change in the coordinate system itself. Now the principal stresses are the eigenvalues of the stress matrix. As you know, this is a 3 by 3 matrix. It's real. So what you are going to get is you are going to get 3 eigenvalues, and these eigenvalues are going to be the 3 principal stresses, sigma 1, sigma 2, and sigma 3. Also, you can see that there are no shear stresses along the principal direction. So what has happened is that this stress matrix has become diagonalized. So what you are doing is you are diagonalizing the matrix. So one of the advantages of looking at the problem in terms of principal stresses is that you can take a certain point, you can think of this point as having a stress matrix, or you can think of this point as having 3 principal stresses, sigma 1, sigma 2, and sigma 3. So we have achieved a dimensionality reduction here from the fully populated stress matrix to a diagonal stress matrix which comprises only of the 3 principal stresses in the problem. Now, like I mentioned before, the matrix here is going to have 3 eigenvalues and also 3 eigenvectors. And by convention, what happens is that the principal stresses can be ordered in this given form. So what we can say is sigma 1 is greater than sigma 2 is greater than sigma 3. So this is just a nomenclature which comes to us by convention. It will help us define certain things such as the maximum shear stress and so on. Now, this is something which is widely used as far as structural mechanics is concerned. So I'm going to give an example later where I'm going to clearly explain what this means. Now, one of the things which can be done with principal stresses is that it can be used to create different type of failure criteria, or it comes into various type of failure criteria. So like I mentioned, the principal stresses are ordered in a manner such that sigma 1 is greater than sigma 2 is greater than sigma 3, and then we can define something known as the maximum shear stress at a point, which will be given by sigma 1 minus sigma 3 by 2. So this is something which is very important. The derivation of this is rather complex. You can find it in many books on aircraft structures or also on structural mechanics. But this formula is very important because this will help us in the Tresca failure criteria. So now one more thing has happened. We have got a further dimensionality reduction. So now if we have a certain point on the aircraft, we can associate only one variable with this, or one scalar, and that would be tau max. So this is something we often try to do in failure criteria, that for any given point we try to have only one number. So remember that at this point we had the stress matrix, then we essentially brought it down to the three principal stresses, and now by using the maximum shear stress we can say that a given point will have a particular number given by tau max, with which we can determine the failure state of this particular point. And if we were to get the entire profile of this tau max on the aircraft, then we could use certain failure criteria like the Tresca failure criteria to see where the aircraft is failing, and at that point we can do some more modification. Maybe we can add more material, maybe we can add a different type of material, maybe we can handle the cross sections and so on, or we can add certain structural members to stiffen or strengthen that part, which will help us to prevent any kind of structural failure from taking place. So let's look at this example to cement this important concept. So here I have given the stress matrix and we have put some numbers here for the stress matrix. So sigma xx is 3 megapascal, sigma yy is 0, sigma zz is 0, tau xy is 1 megapascal, and tau xz is 1 megapascal, and tau yz is 2 megapascal. So we have a typical stress matrix here which corresponds to the stress state at a given point. Now essentially to find the eigenvalue of this matrix, I can set the following determinant to 0. So what I do is on the diagonal terms, I subtract sigma here. So I get 3 minus sigma, 0 minus sigma, 0 minus sigma, and then set this determinant equal to 0. So that's the definition of the eigenvalue of a matrix. Now when I expand this out, I get a cubic equation. So if you do not remember this, you take 3 minus lambda and then you multiply it with this determinant. You take minus 1 and you multiply it with the determinant by 1, 1, 2, 0 minus sigma, and you take 1 and you multiply it by this determinant here. So again, by getting those minors of the matrix and the determinant here, you can find this determinant and you can show that it is a cubic polynomial, and then you can find the roots of this cubic polynomial. Now many a time nowadays, if you have access to software such as MATLAB, or if you are in Python or any programming language, you can often use commands such as EIG or something, which will straight away give you the eigenvalues of the matrix. So it's really a simple procedure. If you have any kind of computational system, maybe even some advanced scientific calculators may help you get that. So now in this case what happens is that there are three eigenvalues, and what I have to do is I have to order them in this manner such that sigma 1 is the highest and sigma 3 is the lowest. So you clearly see sigma 1 here is 4 megapascal, sigma 2 is 1 megapascal, and sigma 3 is minus 2 megapascal. So sigma 1 is greater than sigma 2 is greater than sigma 3. So once you obtain the different sigmas, you have to label them in this manner such that the value which is largest is given by sigma 1 and the value which is smallest is given by sigma 3. And once you do that, you can calculate the value of the maximum shear stress at that point. That would be sigma 1 minus sigma 3 by 2. So in this case, that's going to become 4 minus minus 2, because sigma 1 was 4 and sigma 3 is minus 2. And so this is going to give us 4 plus 2, that is 6 divided by 2, which is 3 megapascal. So that's the maximum shear stress at a given point. Now you can clearly see the dimensionality reduction taking place in this problem from this matrix here, which was a populated matrix with 9 terms, or if we see it as a symmetric matrix, it has only 6 variables here or 6 terms here, 3, 1, 1, 0, 2, and 0. We reduced it to 3 principal stresses here, so the same information is communicated through sigma 1, sigma 2, and sigma 3, and we were finally able to reduce it to only one value here, which is tau max, which tells us that at that point tau max corresponds to 3 megapascal. Now, of course, there are certain failures which take place because of the tau max. So in the Tresca case, we use that. That may be valid for certain type of materials, and there are certain failure situations where you have to consider the principal stresses themselves. So depending on the problem, whether the material is brittle, whether the material is ductile, you may need to use different failure criterias. But do remember that all the failure criterias are somehow based on the principal stresses for the problem. That's why principal stresses are so important, and these are something which many of the modern commercial codes for structural mechanics and solid mechanics try to predict for a given point. So let's summarize today's lecture here. You can see that the stress matrix eigenvalues give us the three principal stresses. So there was a 3 by 3 matrix, and so I got three eigenvalues there, and from there I got three principal stresses. Now the principal directions are the eigenvectors of the stress matrix. The shear stresses became zero in the principal direction, so we clearly saw that there are only three principal stresses, and the shear stresses corresponding to that particular directionality are all zero, and the maximum shear stress is obtained from the principal stresses. This is a scalar measure of the stress state at one point. So let us summarize some of the thinking behind what has been going on. We saw that if we are at any point on the aircraft, we have a stress matrix associated with that point, which is given by sigma and which has all these components. Then we realize that this is a symmetric matrix, so in certain problems we can write this as a vector. And this was convenient for us when we were trying to get constitutive relations and so on. We were able to write this as a vector that helped us get compliance matrices and so on. Now today we realize that if we take the eigenvalues of this stress matrix, we get the three principal stresses, which are sigma 1, sigma 2, and sigma 3. So this is one more condensation, and now from this condensation we can get many different failure criterias and we can use principal stresses there. But also there is one more condensation or reduction that you can do, and that is by getting tau max, and tau max is dependent on sigma 3 and sigma 1. So once again, the values of sigma 1 and sigma 3 can be found, that is the maximum principal stress and the minimum principal stress, and by subtracting them and dividing by 2 you can get the value of tau max, which you can use in the Tresca failure criteria. Now the von Mises failure criteria actually directly uses sigma 1, sigma 2, and sigma 3, and there are some more failure criteria beside that which are also dependent on either the principal stresses or on the maximum shear stress. So depending on the type of material you are working with, the level of conservatism you want in your design, you choose different failure criteria. Now as far as aerospace is concerned, it's very important that the structures be as low weight as possible. So it of course depends on your particular requirement and problem as to what type of failure criteria you are using. But to remember that if you are able to save any weight in the aircraft, then that is something which is very positive in any aerospace system. So that was the lecture for today, where I introduced the very important concept of principal stress, and you clearly saw that principal stress is something which comes directly from the stress matrix. It is nothing but the eigenvalues of the stress matrix. And also we saw that the principal directions are the eigenvectors of the stress matrix, and the principal stresses are very important in various failure criteria, which I will probably discuss next, but maybe I will make a lecture on principal stresses, or rather plane stress and plane strain, before I move to that failure criteria chapter. So I'll end this video now and I will see you in the next lecture. See you then.